Unlocking the secrets of matrix operations. Ever wonder how matrices can be added, multiplied, or even inverted? Join us as we unravel the fascinating world of matrix mechanics. In this problem, A.8, we are given the following two matrices, A and B, which are both with complex entries. In this case, we have reals and imaginaries colliding. That being said, we're tasked with computing the following entities. We're tasked with computing their sum, their product, their commutator, transpose, conjugate, Hermitian conjugate, the determinant, and finally their inverse. And we also need to check that B multiplied by its inverse give us the identity, as it should. Does A have an inverse? Great questions, and this will be an excellent example problem to base all the operations that we've seen time and time again, and or just to refresh yourself if you've haven't seen this in a while. All right, so to start, this is in part A, this is matrix addition. So to add two matrices, as we see color-coded, we need to add them element-wise, meaning if I'm in this position, I add with this element. And we see that in color coding it, we see that this column goes here, add it with the green column here, and so on and so forth. Pretty easy. Just like in vectors where we add it component-wise, x to x, y to y, z to z, same thing happens for matrices in higher dimensions, even higher order tensors. So very, very important there. Now, the next part is a little more tricky. This is matrix multiplication, and as we've seen, multiplication with vectors turns out to be a little more tricky than just scalar operations, right? We have cross products, dot products, outer products, inner products, and if you want to go higher in math, you have the geometric product and a lot of other tools. That being said, to do this, we have to have a way of mixing out all the different element combinations. As such, if we're looking at A and B and their product, what we have to do is be very careful to find a way to orchestrate all the different combinations of the elements. So here's it written out. Now let's take a little dive on how to do this. You've probably heard me talk about row to column before. So we're going to take the first row of A, multiply it into the first column of B, and in this sense, it looks like we're taking the dot product of the first row vector with the first column vector. When we do that, we get the first element of the resultant matrix. And what we'll notice here is that if I do this again, take the first row, put it to the second column, I get the second element of the resulting matrix in the first row. And then, of course, for the third column with the first row, I get the third element in the first row. What we can gain from this is, because it's a row to column multiplication and dot product, we know that the first matrix, in this case A, guides the construction of the rows. We also know that B, the second matrix, guides the construction of the columns. Note that we have 1, negative 1, 1i, negative 1, 1i, negative 1, 1i, negative 1, 1i. So that gives us all the first row of the resulting product from the first row of A. Now we have the first column of B, which is 2, 0i. Note that we have all 2, 0, and I here. 0, 1, 3, this column, and then negative I, 0, 2 here. So in this method, we get the interchange of all the different combinations of the element interactions, and it's a very cool thing to have, and especially if you want machine learning and things like that, optimizing these multiplications is a great way to enhance your code efficiency because as you see, this takes a lot of operations. As such, once we get out all the elements of the resulting products from the row to column dot products, we can see that we can simplify it here. And if you want, you could take a second to write this down. But we see that ultimately it simplifies to another matrix. Now let's take a second to look at it. We had a 3 by 3 matrix in A and a 3 by 3 matrix in B, and the resulting is a 3 by 3 matrix. We know that because if I have an n by n matrix multiplying by an n by L matrix, so long as my inner dimensions match, meaning the n and n on the matrices, my outer dimensions, m and l, are going to be the resultant. Since we have 3 by 3 times the 3 by 3, the two threes on the inside match, and the outer threes are now my dimensions, so we get a 3 by 3, and that's a great check. Otherwise, the multiplication can't happen due to dimensionality mismatch. Now, moving on to part C, we've seen time and time again how commutators play a role in quantum mechanics. And as such, this tells us whether two operators, in this case matrix operators, can commute. Now, generally, this could happen for things that aren't operators but are just mathematical objects. But nonetheless, this tests us how much we commute or how much we don't commute. In this case, we know that matrix multiplication doesn't commute because this will not come out to 0. Let's verify. So we already found AB in the last part. Now we need to find BA. So again, take the row here, multiply it to the column here, and do that for every single element combination. We see this is the result. So 2, 0, -1, or negative I to -1 to 2I. 2 and -1 give us 2. 0 and 2 give us 0. Negative I and 2I give us 2, because the negative I squared goes to positive 1. So we do that for all elements, and then we get this as our result. Note that we have a lot of zeros here, so that's nice. But we did not have a lot of zeros in the AB, so let's see what the difference here is. As a result, the difference we see comes and shows us how much we do not commute. As we see, that first row is full of numbers, and in the second matrix it's not. So we have quite a bit of difference. Again, much like addition, the subtraction is element-wise, so first element, second, and so on and so forth. And then we see that we get a commutator matrix 3 by 3 again, and this shows us how much we do not commute. Very interesting. Now, we have a plethora of operations here that we've seen time and time again throughout the quantum mechanics book as well. The first is the transpose. So the transpose tells us in a nutshell that we need to rotate ourselves or flip ourselves about the main diagonal, which is this yellow line here. But what we see here is that if I want to rotate, this goes to that element, 2 goes to this element, negative 2i goes to this element. We see highlighted in yellow the elements that change over. Well, a different perspective might help is that we're transforming this row vector into this column vector. And if we look at that 2, 0, 3, 2, 0, 3, 2i, negative 2i2, 2i, negative 2i2. Either perspective you want to look at, this is what it's doing. And we need to do this because of dimensionality mismatch. If you studied machine learning or things like that, you've seen often like V times WT. And that's the transpose coming at to make sure we have dimensions that match. Now, its partner in crime, the conjugate, this is just a complex conjugate, things you've seen before, hopefully. And here, all we're doing is changing the signs on the i's. So I have an I here, here, and here. Note that I change the sign. Positive goes to negative, positive goes to negative, negative goes to positive. Of course, these two come together in the Hermitian conjugate. And as you see, we have to combine both the transpose and the conjugate together. So again, we're flipping the elements about this yellow line, but as such, once we flip it, we see the transpose is in yellow, the conjugate is in purple, and we're good to go. So this is used primarily in all the text just to make sure that we have things like magnitudes being computed when we're multiplying two operators together or two matrices, however you want to frame it. Very, very important for quantum theory and a lot of other classes as well. All right, so here is one of the biggest parts of the linear algebra and things that you will use throughout a lot of different classes is determinants. And in part G, this is a determinant, and we use the cofactor expansion method about the most convenient row or column. Now, let's see what this means. So if we're trying to find the determinant of B, which is given here, some complex matrix, then we have the cofactor signs, very, very important. This changes based on how many elements you have And also note that you can only find determinants of square matrices. And what we see is that we want to follow this plus minus plus plus minus plus mesh of signs. And that becomes very important to us. Now, you may have remembered from things like cross products that you had a plus minus plus structure. That's where this comes from because we normally expand about the first row. So taking that lead, if we're going to find the determinant here using cofactor expansion, we have to go ahead and be careful to use a convenient row or column. Since it's common to use the first row, we'll go ahead and use that. And it's common thanks to the likes of cross products or in vector analysis curls. So to do this, we cross out the first row and then we cross out the first column. Now, by crossing out the first row, we give ourselves permission to use the first row signs. So note that we have a plus sign, plus sign, keeping it color coordinated. Now, when we're trying to find the cofactors, these are subdeterminants. And to find the subdeterminants, we cross out the first row, first column, and this is our multiplier. So we have our multipliers of 2, 0, and negative I. 2, 0, negative I. And whenever we cross it out, whatever's left over is the subdeterminant. So we get 1, 0, 3, and 2. That's what we see here. Moving on, if we want to find a second cofactor with our multiplier of 0, which is why we like expanding about certain rows or columns, is because of zeros, we cross out first row and second column. All the remaining elements make the submatrix, or the subdeterminant. So 0, 0, I2. Similarly, our last, with our multiplier of negative I, we get 0, 1, I3. That's what we see here, and we're good to go. Now, because the multiplier is 0 here, we don't even care about this subdeterminant at all. And this is very important to us because if we have a row of zeros or a column of zeros, we know the determinant goes away. And if we have a zero determinant, that tells us a lot about the matrix that we have and whether it's invertible or other characteristics. That being said, now that we have it expanded, thanks to cofactors, we can go ahead and evaluate these subdeterminants. So we see here that this 0 leads us to a nice 0 there, good to go. Now to evaluate the subdeterminant, since we can't break these down anymore, we could use the crisscross method, meaning that I look at the multiplication of 1 and 2, given here, and I minus the multiplication of 0 and 3, given here. Okay, there's other words for this, but you probably remember it was AD minus BC, something like that, with our factor out front. Thankfully, we can go ahead and scapegoat that and not really worry because we can just get this crisscross and finish it up pretty quick. Now for this one, we have 0, 3, and 1 I, so that's what we see here, but with zeros, they cancel out, so we simplify pretty quick. As a result, the only thing left over in this bracket is 2, the only thing left over in this bracket is I, and then we see that this negative and this negative cancel as we see here, leaving us with 4 plus I squared, but we know that I squared is negative 1. That leaves us with a determinant of 3. Now, in the PDF for the patrons, I go ahead and expand about this second row here just because we have two sets of zeros. And once again, we get a determinant of 3, so we're good to go. Now, as far as the inverse is concerned, excuse me. As far as the inverse is concerned, this can be found multiple ways, such as Gaussian elimination by setting an augment to the identity matrix, or via cofactor methods such as this one used in equation 8.57. But just like we saw last time, we have the cofactor signs plus minus plus, minus plus minus, plus minus plus. And we saw that the cofactors themselves, which combine with the signs give us the cofactor matrix, are all these subdeterminants once we cross out the row and column of the element that we're looking at. That being said, we see we have all of the subdeterminants that we ever need, and now we just need to crisscross them and find out what the results are, and then we have our cofactor matrix. As a result, crisscross, we get 2 minus 0, 0, 0, 0 I, so that's our first row, just like we saw last time. Then, of course, if we do this throughout all of them, crisscross, crisscross, and just run them all down, we see we get the results here, simplify the algebra or the arithmetic, and then we get 2, 0, -I, -3i, 3, -6i, 0, and 2. Easy enough. Now to find the actual inverse, we have to take the transpose of this cofactor matrix. So we see that of this result, transposing it about the main diagonal and rotating or flipping, we see the color code here gives us the switched elements. And then we see that the inverse is equal to 1 over the determinant of the matrix itself times the cofactor matrix, which is given here. So that's pretty cool. And this is why if you have a zero determinant, you can't have an inverse, because dividing by 0 gives us infinity. That's not going to happen in math nor in quantum mechanics, where we need to be finite. That being said, this 1/3 is a little weird considering we didn't have any constant multiples last time. But that being said, we have a check for this, which we'll see now. So we know in general that if I compose a entity with its inverse, I'm supposed to get the identity out. Much like if I have f composed with f inverse, I get out f of x composed with its inverse, I get the x variable out, right? Or if I multiply 2 times 1 over 2, which is its multiplicative inverse, I get 1 out. Okay, same thing for matrices. We're supposed to get a matrix full of ones on the main diagonal if this is indeed the inverse. So we have the multiplication here set up for B and B inverse, which also holds for B inverse and B. Okay, so here we see this is good to go, both parts. This 1/3 is a constant, so we can move it out front. And then we do our row to column multiplication, so we're good to go. Note here that we have complex, so just be aware in simplifying. That being said, it looks like -6, +6, positive, negative, zeros, a 3 here, zeros, positive, negative. Ooh, that one's a little different. That one's a little different. Let's see how it cleans up. Sure enough, we see that we get zeros on all the non-diagonal terms and threes on all the diagonal terms. So if we factor the 3 out from all the terms, 1/3 and 3 cancel. Beautiful. And we see that we get a row or a main diagonal of ones. In the main diagonal of ones, we know that that is the identity, so we are good to go, and this is indeed the inverse. There's a lot more to be said about determinants and what they mean in terms of the space and how they scale the space, things like that. Determinants are very geometric in their meaning, and if you've taken a vector analysis class, you know that they lead to things like areas, volumes, and various other attributes, and they are heavily dependent in a lot of things we do. That being said, since we know the importance of determinants, we can go ahead and test to see if A has an inverse. And we could check this via its determinant. So once again, if we lead with A, we want to highlight where the zeros are. And the 0 here happens about the second row. Okay, so we're going to want to use that row or the second column because of the 0. Keeping in mind the rows, we're going to have negative plus negative, or if we use the second column, we'd have negative plus negative 2. Doesn't really matter. As a result, because of that 0, we're going to use its convenience and expand about the second row. Setting it up like we did last time, because the determinant's 3 by 3, we need to break it down to subdeterminants of 2 by 2. Same thing would hold if you have it a 4 by 4 or 5 by 5, but they scale almost exponentially in their operation, so probably don't want to do those. That being said, since we're committed to the second row, let's go ahead and cross that out. We have our negative plus negative structure from the cofactor signs. Our multiples are 2, 0, and 3. Thankfully, the 0 cancels everything out. If we want to find these subdeterminants, go ahead, cross out the first column. Then we're left with 1i, -2i2. That's what we see here. Then go ahead for the second scale or the second subdeterminant, cross out the second column. -1i, 2i2. That's what we see here, though it doesn't matter. And then we see that we cross out the third column. We have -1, 1, 2i, -2i, which is what we see here. And now we're good to go. Since we can get rid of this, we don't care about it because it's 0. We can go ahead and do crisscross on everything else. So 1 to 2, I to -2i with the minus sign. We see those two minus signs cancel. This 0 doesn't do anything. And then we have our -3, -1, -2i, negatives cancel. 1 to 2i, we're good there. Clean this up. We see that I and I give us a -1. That's what we see here. So 2 minus 1, that goes to 0. Then we have inside this bracket 2i minus 2i. Guess what? That goes to 0. So we have -2i times 0 minus 3 times 0. Guess what? That gives us a big fat 0. And because the determinant is 0, there is no inverse for a. Now, there's a lot of other things to be able to test for invertibility and what it means, but especially if we're talking about a linear system of equations. This means that the system's not consistent and there's no solutions, things like that. The applications are far more than what we're going to cover in this appendix, but if you want to talk about more of the applications in the linear algebra theory, I'll probably do a playlist on just linear algebra because, quite frankly, it runs the world right now. Look at AI, look at machine learning, etc., etc., etc. This is very, very important for everybody's day to day, whether we want to pay attention to it or not. Whew, that was a fun video. So if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone is interested in joining or in supporting the channel, joining our Patreon community, you can check the link in the description below. Together, we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.